All right. Okay, so I think what we'll do, I'm going to go ahead and keep going on with collisions today and with center of mass and some relative velocity stuff to make sense of the center of mass coordinate system. I'm going to show you why that's useful to think about the center of mass coordinate system. I think Thursday's lecture is probably just going to be devoted to Q&A about any last-minute questions people might have about the exam. We might talk a little bit about torque at the end of the lecture today. I might talk about it next time, depending on how many questions I get, sort of get started. We're going to hit torque full on next week. Torque will be the big topic. Rotary motion, we'll get into that kind of stuff. So today we're finishing up more Chapter 9 stuff. Chapter 9, and we're doing center of mass. Center of mass system. Why is that useful? And then I have another one of these crazy demos with the ballistic pendulum. We'll do some stuff with that too. Okay, so last time, because it's hard to see, maybe I'll work on this board over here. Last time, what we talked about was the ballistic pendulum that was vertical. Remember that? So we had the gun facing upward. It was anchored to the floor. We had a block of wood on top of that. You guys all watched. Pulled the trigger. The bullet got lodged in the wood. The wood flew up in the air with the bullet still lodged inside. And you all saw how high it went, and you were happy to fudge the number to make my calculation easy at the board. It was 0.8 meters, right? And from that, thank you. From that, oh, by the way, this is Roberto. He actually takes care of all the demos. This thing's working up here, so he's the one who actually makes all this stuff. He's the one who actually, yeah. So when it goes south up here, it doesn't work out. That's my fault. But when it works really well, it's because he's back there making it work. Anyway, just to let you know what's really going on. All right. So what do we do? We said we had 3 times in the problem. So I'm just going to jog your memory. And then we're going to think about what happened to the lost kinetic energy and how much was lost. How much kinetic energy do you lose during an inelastic collision? And what do I mean by maximally elastic? All right. So here we go. At T0, we said we had the gun facing up. What the hubbub? Actually, do people have questions before we get started about test-related stuff or whatever? Just in case. Nothing? All right. Okay, cool. So I got the gun, I got my piece of wood, I got the bullet that's still inside the chamber, hasn't started moving yet. And then at T1 we said, okay, the bullet's moving. We said, this is a 1. We'll call it V sub B1. V for bullet, 1 for the time, right? All right, very good. And there's smoke coming out because the gun is fired. This thing's moving. The wood is not. And then we had T2. We said, oh yeah, now the wood and the bullet are moving together. I gave that another V, a capital V with cerise on it, just to distinguish it from this. And I say, all right, my gun is still anchored to the ground. So the gun never moved in this case. We're going to have a different situation here. I'll have to think about that. But in this case, the gun was anchored to the ground. Right? It was as if it was part of the earth. Is the way to think about it. That's important. Okay, and then finally what happened was we had, oh yeah, T3, 0, 1, 2, 3, got it right. And then this guy's up in the air. I didn't give myself a lot of room here. But okay, I went up to an extra height H, right? Okay. And so we said, if we went from here to here, how do we do that? Was that, did we use conservation of energy or conservation of momentum? From time 1 to time 2. Yeah, the bullet's moving here, the wood's not. Then there's a collision. The bullet and the wood collide, right? And they stick together. So was it elastic or inelastic? Inelastic, right? Kinetic energy was lost. We'll calculate right now how much. And so we use conservation of momentum here. Or maybe I'll use center of mass, conservation of momentum, P for momentum, right? And then from here we use conservation of energy. And that was okay. Now kinetic energy wasn't conserved here, right? We started off kinetic energy and we had some other kind of energy over here. What kind of energy did we have at the end of this process that we didn't have before? Yeah, it changed the potential energy to gravity. Now, the 0 point for that is arbitrary, so you could say this had negative potential energy to gravity and this had 0 potential energy to gravity. These could both be negative, both be positive, but the difference is not up to us, right? The difference has to do with the fact that there's a change in H. It's higher here, so is the potential energy greater or less at T3? Yeah, potential energy is greater because it went higher. That's right. So is the work that gravity, this is relevant for Thursday, right? Is the work by gravity positive or negative? The work of gravity on the bullet wood system. Was the work of the gravity on that positive or negative from time 2 to time 3? Who thinks negative? Work due to gravity was negative. Who thinks work of the gravity was positive? I heard a couple positives. I see a couple hands. Yeah, so it's negative. The work of gravity is negative because the motion was up, but the force of gravity was down on the object. But that means that there's an increase in the potential energy due to gravity. All right, very good. So we worked all this stuff out, and when all the dust settled, right, I could reproduce the algebra. But essentially, yeah, conservation of momentum here was, we sum up all the MVs, make them the same before and after. You said, yeah, there's some external force to gravity here, but it's such a short period of time that the impulse was very small compared to the change of momentum due to this really harsh collision between the bullet and the wood. And then we got a different equation over here. Conservation that was 1/2 MV squared before and after, right? And when all was said and done, we wound up with, let's see, how much do I need to write down so we can use it? Well, first of all, we figured out, oh, what the heck, should I write all that? I'll just write real quick, just to make sure everybody's on the same page. We had mass of the bullet times V bullet 1, right, has to equal, this is just conservation of momentum, right, mass of the bullet plus wood. But remember, the wood was 100 times more massive than bullet. So I can neglect this and say, well, I'll say this is much less than M wood. Right? I can neglect this whenever it's added. I can't neglect it here. I can't set this thing to 0. But I can set this to 0, no problem. These add-ons mean it's much bigger, right? And then I say, oh yeah, with velocity 1 here, I want the thing I call capital V. So that's just conservation of momentum at this time step right here. And then for this guy, what do I have? For that, I've got 1/2 M wood plus M bullet. Again, sum. We could get rid of this right here, but it's not going to matter. It shows up in the same way on both sides of the equation. So I've got V, capital V squared. And I said, oh yeah, and that equals, change, oh yeah, MGH. Oh, what jam do I need? Well, the whole thing went up. The bullet and the wood went up a height H. So both the wood and bullet have to appear here in mass, right? That's why this cancels out. It doesn't matter. I don't have to worry about the fact they have differences. Here it makes a difference. It makes our calculation easier because this doesn't go away unless I do that. Okay, great. Oh, and in fact, I should be careful how I say that. This doesn't cancel over here after I do that. This is mass of wood. That's mass bullet. In fact, if it weren't for that, it'd be a very different problem. And we're going to talk about that in a minute. Why have small bullets? Why do you buy bullets that are, I don't know if you do, but why does someone buy bullets that are much smaller than a rifle? Why is that a good thing? And for that matter, what was it like shooting a cannon? In the old days, people had cannons on man of war, giant ships in the ocean, right? And the cannonballs were comparable in mass. They weren't as heavy, but they were comparable in mass to the cannon. So what are the consequences of that? I mean, the main consequence I'll just tell you is there's a lot of recoil, right? You don't stand behind the cannon when you fire it. Whereas that's not, the recoil for this guy's not so bad, right? And we'll work that out. So, all right, so there's this, and then, oh yes, it's MGH I want. So I want G here, and I want H. By H I mean this H, the delta H, right? Great. So then I thought, oh yes, now I can solve for capital V. That's just equal to the square root of 2GH. Right? This is a single equation you've seen a million times when you start from rest and you wind up some non-zero velocity, or vice versa. You drop, it's the other way. You start off with some non-zero velocity and then come to rest. That's just the opposite of dropping, but it's the same equation. You just swap between by forward and backward. So if I now isolate the thing I want, VB1, and say, oh yeah, that's just going to be mass of wood over mass of bullet times capital V. Oh yeah, we solved that over here. That's just mass of wood, mass of bullet times square root of 2GH. Right? And if you plug all these numbers in as we did last time, it turns out, remember, the wood's 200 grams, the bullet's 2 grams, so it's a factor of 100. That's 10. That was 0.8 meters. Okay, so it all turns out to be 400 meters per second, which is about 800 miles an hour, roughly a little faster than sound. So you see that the velocity of the bullet is way faster than the velocity of the bullet lodged in the wood. Right? By a factor of the ratio of the masses of this big massive piece of wood and a little tiny bullet. And the same is true for the gun. So we didn't actually do this case, right? But if we did this case, if we thought about well, actually, it's a little bit. So we're going to think about that in this context. In this case, the gun is actually anchored to the ground, so we didn't have to actually measure the recoil of the gun. We were keeping that out of the process. But it's the fact that when you have a collision, the difference in the velocities goes like the ratio of these masses. That's really the crux of why you want to have a small. Well, if you're the shooter, right, you want a small bullet in your gun because you don't have a big recoil. You want a very small momentum towards you. The momentum are the same, right? Momentum's conserved. You want a small energy, a small kinetic energy. Kinetic energy goes like v squared, right? So if we ask, and so let's ask, how much kinetic energy was lost here? So let's calculate that. What is the change in the kinetic energy? And let's do it from time 1 to 2, t1 to t2, right? So if you're going from t1 to t2, the kinetic energy change is just going to be, well, let's see, it's going to be the final minus the initial. So it's 1/2. What is the initial? This is final. Sorry, final kinetic energy. Well, it's the mass of wood plus mass of wood. But we can ignore the mass of the bullet if we add them together, right? So I can say, oh yeah, that's really small compared to the mass of the wood, right? Times v squared. And what v1 with a capital V. And I'm going to subtract the initial velocity, right? The initial velocity was, or kinetic energy, excuse me, is 1/2 mass bullet times v. What is it? Times 1 bullet squared. Did I get that right? That's right. So it's final minus initial. Great. And so what? Oh, yeah, so I plug this in. Well, we just figured out that the ratio we could write down capital V in terms of the thing we got right here, VB1. It's just 100 times that. Right? Oh, sorry, forgot to square it. Crucially. Right? So we get a mass of wood. Oh yeah. So let's do this. Let's write everything in terms of mass of bullet and everything in terms of the velocity V1, just so we can compare these two terms. So if we do that, well, as we just said, the sum of the two masses right here is the same as just the bigger mass. It's 100 times bigger. We can neglect that. We can write this as, oh yeah, that's just 100 times the mass of the. Well, let's do it this way. Let's do it this way. What is V? It's V1. Oh, yeah, so I see. Let's do it this way. So we can just see what happens. Well, this gets squared, and this gets squared. So what I just did was I substituted in that expression right there. Oops, I think I did. MV over MW times VV1 is capital V. I squared it. And it's squaring, and I get the square of the prefactor, and I get the square of that, right? And then I subtract this. Okay, 1/2. All right, okay, that's the same thing. I already have it. So I want to see how this thing compares to that, right? Well, what you can see is that it's the same thing. This is the same expression with a factor in front. And the factor is MV over, no, sorry, MW. What is it? 1/2. And let's just write that thing here, MV V1V squared. So that's the thing I want, right? I pull that out, then what's left? Well, there's one up top and there's two on the bottom. It means there's one that survives on the bottom. So and there's one extra on top. Does everyone agree? Does that look right? Which equation do you not like? The one on the bottom or the one up on the top word? So here's what I did for velocity. I said, all right, I got v squared, capital V squared. I can rewrite that as little v squared times mv over mw all squared. So if I were substituting in for lowercase v, if this were vv1, if I substituted in over here, in other words, so if I substituted in for here, this expression, then I'd have it mw over mb. But what I chose to do is to substitute in for the capital V. I think that's mb over mw. You like that? So I did a couple steps in my head, and I know that usually spells disaster. But I think that I got it right, and we'll know for sure when we look at the numbers. So if I want to know how much kinetic energy was lost, or what the change in kinetic energy is, what I find is, so first of all, mv over mw, is that a big number or a small number? Small. It's 0.01, tiny. So this is actually -1. It's saying that I lost, and this is what the initial kinetic energy was. So the point is that almost all, 99% of kinetic energy was lost, but not all of it, right? But almost all of it. And so if I ask the question, well, is it maximally inelastic? The answer is it is maximally inelastic. Maximally inelastic means that as much kinetic energy was lost that could have been lost, right? So the way to understand what's going on there is to consider what's happening in the center of mass coordinate system. If you view this collision in the center of mass coordinate system, what you would see is that all the kinetic energy is lost. But the initial kinetic energy wouldn't be the full amount of kinetic energy we measure in the laboratory frame. It'd be different. So one thing that's weird about kinetic energy, if you like, is that it's different depending on what coordinate system you measured it from. Because the velocities are different. If I change my coordinate system, the velocities of objects are different as I measure them, right? I'm walking along, just like the apple on the bus. I throw the apple on the bus. If I ask with the coordinate system that's nailed down to the bus, right? Which I can do and still use Newton's laws as long as the bus isn't accelerating. As long as it's going in a straight path and it's not speeding up or slowing down. And I say, okay, what's the kinetic energy of that apple? Well, if I threw it at 10 miles an hour, I'd square 10 miles an hour and multiply it by the mass of the apple and multiply half, and that's kinetic energy as measured by me on the bus. But something on the ground watching the 60 mile an hour bus go by, plus the apple inside, so the apple's going 70 miles an hour, right? As you all correctly tell me whenever I ask you about that problem, from the ground, the kinetic energy as measured by something on the ground is different, it's bigger, right? So keep that in mind when you're calculating kinetic energies. And the fact that it goes like a square means that when you have collisions and you're conserving momentum, right? So you're trading off velocity of one thing for velocity of another, and mass is coming into play. Which if you wind up losing, if you lose kinetic energy, it can be a lot in this case, but it'll be all of it if you look at the center of mass. Now it's a little tough to think about this system from the center of mass coordinate system because the center of mass is moving really fast. The center of mass is moving upward in this problem pretty quick. But we can think about problems on the air track that are a little simpler, where the masses are comparable to each other, so the center of mass is moving at a speed that's intermediate between the two speeds of the object, right? So we can work it all out. But the main thing I want to show you is that if you have a tiny little bullet and a big piece of wood, and conversely, if you've got a small bullet and a big gun, right, then the kinetic energy that's like if you fire a gun and the bullet comes out very small compared to the gun, the kinetic energy is all in the bullet, not in the gun. That's good for your shoulder, right? That's a good thing. If you're skeet shooting or whatever. But if you have comparable masses, then they both get equal kinetic energy, and you want to do as much. You can do as much damage to yourself as you can to the little, I don't call it skeet, the little thing that gets shot in skeet. What do you call this thing? Sorry? Clay pigeons. Yeah, that will not be on the exam. All right, but yes, the clay pigeon. That's right. All right, great. So good. There is a lot of kinetic energy for an inelastic collision. Let's think it through and think about it from the center of mass coordinate system with the air track. And let's consider first that simple case we always start with, where the two masses are the same. All right. So let's turn this thing on. All right, I think I'm hooked up. Let's see. It's a little bit loud. So I'll do the same thing I've done before a couple times, and then we'll look at it a different way. I'm going to have two equal masses. I'm going to bounce one off the other, right? And you know what's going to happen, right? In comes this guy. These are the same mass if I've got the right two. He'll come in with a non-zero initial velocity. He'll have zero initial velocity in the left, right? And then after they collide, he'll get all the velocity and he'll be holding still if things are balanced properly in the rest of it. So let's just remind ourselves how that works. All right. Sure enough, well, that works really well. Look at that, right? Very good. So every one of those collisions was perfectly elastic, right? So now let's think about how this looks. Well, let's draw it out, and then let's think how it looks from the center of mass. So if I draw that in the lab frame, oh, and I've already lost my shot. Here we are. If we draw that from the lab frame, let's draw it right here. So we have an incoming mass right here. This is A coming in this way. It's got some, and this is T0, right? So T0, T1, T2, right? Here comes A moving to the right. And here we'll do this. Do that, right? All right, so it's coming in, and then B is sort of sitting still, waiting around. Nothing's happening yet. We'll start off with, we'll assume that MA equals MB for this problem to get started. So here's the initial velocity 0. We'll call this VA 0. So 0 indicates time, A indicates which object I'm talking about. Now they collide, and I've given this a name. I didn't have to, but just so it's clear to everybody what's going on. Right, here's where they collide at T1. And you know what happens. B comes flying out the other side, and A holds still, because it's an elastic collision. So VB2, we know the answer we calculated last time, equals VA0, right? Same sign, same magnitude. And this guy has 0 velocity. He's not moving. A is not moving, right? So where's the center of mass throughout this whole process? If mass of A, so for this problem, let's assume that, and we'll just assume, we actually used this when we did the calculation to solve for this. So mass of A equals mass of B for this problem. We'll just call it M, right? Because it's the same in this problem. In this case, where's the center of mass? Well, it's clear where the center of mass in this case is right off the bat, right? It's right here where the object. They're at the same location in space if we assume they have no spatial extent. Even if they do have a little spatial extent, well, it's right between them because it's the same mass. So here's the center of mass right here. How about in this case? Well, whatever distance this is, right, it's halfway between them. Because these have the same mass, and if we calculate the center mass, you know, R equals the sum of M sub I times R sub I, all divided by the sum of the masses, right? You wind up with the center mass right here. I'll label it center mass. Does everyone agree? Is the center of mass moving right here? Yeah, absolutely. This guy's not moving, but he is. And so if you calculate the center of mass at different moments in time, it'll be moving. It has to, right? Because the center of mass is always halfway between these things. So we could also say, what's the velocity of the center of mass? Oh, it's just the weighted sum of the velocities of the objects, right? Mass times velocity equals 0 plus mass of A times velocity of A, right? And then you divide by the sum of the masses, which is 2m. Oh, so what is the velocity compared to the velocity of A at time 0? Bigger, smaller? Yeah, how much smaller? Half. Absolutely. Because in this problem, these guys have equal masses. So you know that's always in the middle. And that means that as this guy moves to the right at some velocity, 1 meter per second, whatever it is, he's going to be doing half a meter per second. He's always halfway between the two. And then sure enough, when they collide, center mass is right on top of them. And similarly, after the fact, center mass keeps moving to the right by half the velocity of the initial velocity of object A, right? So we can actually see that the center of mass is following, I didn't draw a very good line, is following a constant acceleration. Actually, what is the acceleration of center of mass? Is it speeding up, slowing down? Zero acceleration. So yeah, not only is it constant acceleration, it's constant velocity. The center of mass has constant velocity. And it has to, right? Because F net equals ma of the center of mass, where F net is the total external, all the external forces summed up acting on our system. What's our system? If we mean our system to be A and B together, this is the center of mass of that system, well, it's moving, it's not accelerating. Once you know its initial velocity, the center of mass must maintain that the whole time, unless an external force comes into play. Like when this thing bounces off the wall or something, or if I can put my hand on it or something like that, then it changes, right? But provided there's no external force, these are only internal forces between objects within the same system, then the center of mass, its motion, right, obeys constant acceleration. Excuse me, is that right? No, it's not, well, stronger. Constant velocity. It's not changing. Yeah, so there you have. So what does this look like if we redraw this whole scenario and we do it from the center of mass coordinate system? What does that mean? It means that we come up with some new coordinate system. I'm going to use primes for that coordinate system to describe variables that are measured in the center of mass coordinate system. And let's think about what that looks like. So I'm going to do this thing again where this guy comes in. But what I'm going to do is I'm going to put myself, as the intrepid experimenter, I'm going to put myself at the center of mass. I'm going to walk along at half V, A, and 0, right? Right at the center of mass. And I'm going to observe what it looks like to me. What's it going to look like? Are the objects going to be moving? Well, he's already moving in the lab frame. He's moving, and he's not. In my reference frame, they're both going to be moving, right? So let's watch and see what that looks like. So he's holding still in the lab frame. He's moving in the lab frame. I'm going to put myself right between him and walk along. There I go. Bam. Right? All right, I'm still moving. And what do I see? As I walk to the right, I was moving half as fast as this guy was at the end, but he was still getting away from me. In my reference frame, that guy was moving away from me to your left. But how about the one who was holding still at the end, right? So at the end of the process, I'm still moving, and he stopped. So from my perspective, which way does he appear to move? Actually, from your perspective, sorry. So in terms of direction, I'm using your perspective. In terms of the 0 point of the origin, let's use my perspective. Just to make it complicated. So I'm walking this way. For you guys, if you were walking with me this way, would you see this one moving to your right or your left relative to me? Your right. That is correct. Say it that way. So if I'm moving along like this, trembling at 50 miles an hour, however fast I'm moving, then that guy's going that way relative to me. He's holding still with respect to the the track, the room, the coordinate system he started with. But when we convert all this into a reference frame that's anchored at the center of mass, then both objects are moving at all stages of the whole process, except I guess at this moment when they're colliding and they come together, right? So what it looks like from the center of mass is this. Object A, so we'll drop from your perspective again, except that we're moving the center of mass coordinate system. But in terms of left and right, it'll be the same in this picture. So A is right here. He's coming in this way. He's not moving as fast. He's only moving half as fast as he was before. So now we've got V prime indicating that this is the center of mass coordinate system, right? A 0. So A still means object A. 0 still means time 0. When you get into relativity next semester, if you wind up taking AP, you'll find out that these equations have to be modified. Time and space get all jumbled up in a funny way. It's one of the, I think, one of the most interesting topics in all of human thought, and certainly in physics. But in this class, we're spared time to worry about relativity. We can just add velocities and it works out fine. We can just use relative velocities to subtract them off. So sort of a fun aside for those of you who enjoyed it. And the rest of you, I apologize. Okay, so A's going to the right, B's holding still. That was in that frame. Now B is moving which way? In the center of mass coordinate system, which